to quantum numbers. So today what we're going to do, hopefully this is just really easy for everyone because it should kind of tie in with the electron configuration, which we've been working on quite a bit. So remember now that Schrodinger, he came up with a mathematical approach for finding the probability of finding an electron. Well, that mathematical equation, the solution to that equation, yeah, we talked about it in terms of electron configuration, but we can also look at it in terms of assigning quantum numbers to electrons. So quantum numbers are really just a way of giving an electron an address. So it's a way of assigning an address to an electron within an atom. So every single electron within an atom has 4 unique quantum numbers to it. And this is going to be kind of a reoccurring theme that you'll see as we go through these, and I'll try and bring this up again. But remember that each of these numbers determines the possible allowed values for the next quantum number. So that's what you're going to see with this, that each quantum number is dependent upon the previous quantum number. And there are 4 of these quantum numbers that we're going to look at. They are listed here, and let's just go ahead and start with our first one. And the first one, you know it already because it's exactly the same thing in electron configuration. So the first quantum number is n, which is known as our principal quantum number. It tells us the distance from the nucleus. It tells us the energy level. It's analogous or equivalent to what Bohr called his orbits. So in other words, it is that distance from the nucleus that we're seeing. Now, what you'll see on your paper, I put in blocks on your notes. It's kind of boxed in. You will see that there's a place where it gives you the allowable values. So for n, we see that n can equal anywhere from 0 to infinity. So that's what we would expect. And they're always going to be whole numbers because, again, we're talking about energy levels. You can have it as 1, 2, 3, etc. Okay, pretty easy for that first one. That's what your n is equal to. The second quantum number is known as L, and I tried to be, on these notes, I tried to make sure it was really obvious that it's an L and not a 1 on there because depending upon the fonts you use. But L tells us the shape of the orbitals. In other words, it tells us the sublevels. The fancy name for it is that it is the azimuthal quantum number. So our second quantum number is L. It is the azimuthal quantum number. Now we've looked at these different sublevels, these different shapes of the orbitals, and what we've seen is that we have these things called S, P, D, and F. Well, we can assign quantum numbers to those. And if you were to follow Aufbau's principle, we would see that, yeah, you fill up your 1s before moving to your 2s, before moving to your 2p's, before moving to your 3s, etc., and we can keep moving on with that. Well, all of those different sublevels have quantum numbers associated with them. So L has values anywhere from 0 to n minus 1. So make sure you see that on there. Again, notice that this quantum number of L, our second quantum number, is dependent on the value of our first quantum number, of what n equals. So that's what we end up seeing there. When we assign these, we know that our different shapes, remember S, P, D, and F. So the S, we're just going to give values to them. The S sublevel has an L equal to 0. Then we have the P, where L is equal to 1. A D, L is equal to 2. An F, L is equal to 3. So let's go ahead and make sure we have this written down on our paper. I think you've got it written down, but you might want to box it in or something, put a star by it. What we see is that S is equal to 0, P is 1, D is 2, F is 3. So what I just showed is increasing energy or increasing complexity of those orbital shapes, or those sublevels. So now, if we know what sublevel it's in, then we definitely know what our L is equal to, what our second quantum number is equal to. All right, the next one M sub L. This is known as the magnetic quantum number, and what it does is it tells us the orientation of the orbital about the nucleus, so those orbitals within that sublevel. If we were to look just at the axes here, and maybe my example, you don't have to draw this down, but maybe my example is going to be a p sublevel. Well, I can have an orbital on the x-axis, I can have one on the y-axis, and I can have one on the z-axis. So that's really what we're thinking about, is the orientation of those orbitals within that sublevel around that nucleus. And what we see is that those values can be anywhere from negative L to positive L. Again, this quantum number, m sub L, is dependent upon my previous quantum number of L. So it's anywhere from negative L to positive L. We just saw that L, if it's an S, I'll write this down, S, P, D, and F. This is not written on your notes. If you want to try and find a little place in the margins to write this, that might be helpful to help you visualize what this really means. But for an S, P, D, and F, we've learned that our second quantum number, L, would be equal to 0, 1, 2, and 3, respectively. So for our M sub L, well, we know it's going to be anywhere from negative L to positive L. So what that's going to mean, in this case, if I've got my S or sublevel, I know that my M sub L is going to be anywhere from negative L to positive L, so negative 0 to positive 0. So the only possibility for my M sub L is that it's equal to 0. Well, I could do the same thing for my P. I know that my L is equal to 1, so my M sub L is going to be equal to anything from negative 1 to positive 1. I'll write that down, negative 1, 0, positive 1. We could keep going. We could do that for our D block. So if your D, your L equals 2 for your D, that means your M sub L is going to be anywhere from negative 2 to positive 2. Negative 2, negative 1, 0, plus 1, plus 2. We could do the same thing for our F. We see it's anywhere from negative 3 to positive 3. Okay, big picture. Again, remember what we're doing. We're now on our third quantum number, and all we're doing is we're trying to figure out a numbering system to be able to give each and every electron within our atom an address. Where is it located? Where does it live? So getting this kind of visual might help you in understanding what M sub L is equal to. You know, another way that you might think about it, instead of thinking about those orbitals from our orbital spin diagrams, maybe you can envision a periodic table. You always have one of those in front of you. Your S block, right here, you've got one orbital. You can fit 2 electrons in it. Well, what we end up seeing is that since this, our L is equal to 0, your M sub L is going to be equal to 0. Over here in your P block, since your L is equal to 1, your M sub L is going to be anywhere from negative 1 to positive 1. Negative 1 to positive 1. Here in your D block, which is equal to 2, it's going to be equal from anywhere from negative 2 to positive 2. And we repeat it. And same thing with our F block, which is equal to 3. It's going to be anywhere from negative 3. I don't know if I need to go through all of this here. Plus 1, plus 2, plus 3. And then we'd repeat it, negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3. Okay. We're going to write this down here a little bit on the back of that periodic table. But that just kind of gives you an idea as to what we're looking at for our orientation of that orbital around the nucleus. Okay, last one, our magnetic spin number, M sub S. For this is just going to tell us how that electron is placed in the orbital. So you guys have already been you're pretty versed in drawing orbital spin diagrams. So you could probably picture, you know, a p sublevel. And when you place those electrons in there, you know it's up, up, up. Well, all of those have the same spin. Our allowed values for magnetic spin, this is the one that really doesn't even relate to your previous quantum number. The only possibilities is that it's going to be a plus 1/2 or a minus 1/2. That's it. It's spinning in one direction or the opposite direction. So all of those up arrows, this is what you're going to want to write down. Your up arrows, we're going to say, are equal to a plus 1/2. And your down arrows are equal to the minus 1/2. So what we've just done in this orbital spin diagram, up, 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 so we've given that fourth quantum number, every single one of those electrons, the fourth quantum number is a plus 1/2. Now when you come back for the next three, down, 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 those all have minus 1/2 for that fourth quantum number. Okay, so you guys have just gotten a taste of what all those four quantum numbers are. Now what we're going to do, we're going to skip to the back side of your notes where it says to go ahead and put some of this information in a tree diagram. And for this, I'm not quite tall enough to reach this very well, but here I'm going to show my N, my energy level. Over in this next set of blanks, I'm going to go ahead and show my L. And then in the last set of blanks, I'm going to show my M sub L. And so we know N equals energy level. Up to you if you want to write that up there just as a little reminder. L equals your sublevel. Well, remember, L can be anywhere from, it can be anywhere from 0 to N minus 1, right? And then we know that our M sub L is going to be anywhere from negative L to positive L, just as a little reminder. Okay, so if we're looking at our energy levels, I'm going to do examples here for our first 4 energy levels. And remember, you have a periodic table in front of you all the time anyway. So if for some reason you got to a test or something and you said, oh, the first energy level, I don't remember what sublevels there can be in that first energy level. You would just come over here and you'd go, oh, the first energy level. And of course, we have to pretend helium is right next to hydrogen there. But that first energy level, you would look and see that all you have is the you have the S block that's in there in that first energy level. So you've got an S. I'm going to make myself a little note of that. That's all that's there. In the second energy level, we know that we've got an S and a P. So I'm pointing to the periodic table right now, looking and seeing I have that chunk, the lithium and beryllium in the S, and I've got boron through neon in the P. Those are both in that second energy level. So you have an S and a P that exists in that second energy level. So we could keep moving down, and hopefully that's pretty ingrained in you guys right now. All right, so now I have not written the quantum number for that. I was just writing myself little notes. That means that my L is going to equal, if for an S, I know that my L is going to be equal to, what do you guys remember? What's the L equal to? 0, good. And here, for my P, the P is always going to be equal to 1. So we have 0, 1. The D is equal to 2, and the F is equal to 3. So that just goes back to that idea that we said S, P, D, F. Your L is equal to 0, 1, 2, and 3. So we looked at that and we put a star around that. So that's all I've done now. So your M sub L, remember, is going to be anywhere from negative L to positive L. So I have to look at my L. If it's equal to 0, it's going to be anywhere from negative 0 to positive 0. So 0. That's the only possibility. So we just answered that. If your L is equal to 1, your M sub L is equal to anything from negative 1 to positive 1. if your L is equal to 2 for a D block, then your M sub L is equal to anything from -2 to +2. And finally, if your L is equal to 3, your M sub L is equal to anything from -3 to +3. Okay, so there's our little tree diagram. Of course, notice what we didn't put in here. We didn't say anything about our M sub S, and that is your magnetic spin. Again, remember that your +1/2 is equal to that up arrow, the -1/2 is equal to that down arrow. So you just have to think about which electron this is that we're referring to. So if I were to look at something like oxygen, atomic number 8, there are 8 electrons in there. So there would be 8 sets of 4 quantum numbers, that each of those electrons would have one of those sets of 4 quantum numbers. But we could assign 4 quantum numbers to each of those 8 electrons. Okay, so here we have on the front side again, we have this table. You guys have seen this. We've done this. We did this the first day with the electron configuration, put a little star by it, and we said if you understand this, it'll kind of help tie in a lot of things about electron configuration and quantum numbers. So let's just look at this again. Our sublevels we know are S, P, D, and F. How many orbitals, when you draw those boxes for your orbital spin diagrams, how many do you draw for an S? 1. What about a P? 3. D? And F, 7. Hey, there can be a maximum of 2 electrons per orbital. So what would you expect? Maximum number of electrons in your S? 2, 6, 10, and 14. Again, let's pretend you have a freak out moment on your test and you don't know, you can't remember this. You have that beautiful periodic table in front of you always, and it tells you the answers. It's got everything you need on there. You just have to know how to read it. So in your S, I'm stretching over here to the periodic table, we see that we've got 2 electrons that can fit into your S. You've got 6 that can fit into your P, 10 that can fit into the D, and you've got 14 that can fit into the F. It tells you all that up there. Okay, let's do it in another way. Let's do it by energy level. First, second, third, and fourth energy level. What sublevel, there's only one, what sublevel can you find in your first energy level? S. What can you find in your second? What about your third? SPD, and fourth is SPDF. So again, if we think about the number of sublevels, so we just answered it right here. We've got 1. Here we've got 2, 3, 4. But what about the number of orbitals? We just did that on the previous little table. So you know that there's 1 box for your S. Your P has 3, so 1 plus 3 gives you 4. Here we've got 8, and here we've got, I can do this. Here we've got 16. That's hard math. There. Okay, so, wait, did I do that right? No, yeah, okay. That's why the math was so hard. It's really, it's not tough stuff. So we've got 9, and then this is 16. So finally, for our maximum number of electrons, again, you've got 2 electrons per orbital. So you see 2, 8, 18, and 32. I think I actually multiplied correctly on that one. So here, when we come down and look at our formulas that we have, you see if you, for any energy level equal to n, then you're going to have n sublevels. It's always the same number. Okay? Your number of orbitals, what's the formula for that? N squared. And finally, 2n squared for your electrons. Okay, looks good. So hopefully you're having maybe some aha moments where it's all kind of getting tied in a little bit together. So now what I want to do is I want us to think about, and this is just showing you a little bit of electron configuration with the periodic table, but I want us to turn to this, which is on the back of a periodic table. And we're going to assign a legend or a key for all of those 4 quantum numbers. I'm not going to fill in every little bit of this, but I'm going to fill in lots of it. So if we were to say, I'm going to do my 4 quantum numbers. 1 is N, 2 is L, 3 is M sub L, and 4 is M sub S. If we wrote those down. And I'm going to try color coding these, I guess. We'll do N is just going to be our energy level. I'm also going to put this guy here. And I'm going to get rid of this guy. All right, so this looks like it is energy level 1. That is my first period. That's it. Down here, energy level 2. And I can go across here to the P's. And I see this is the second energy level. Are there any other second energy levels? No, we just covered them all. Okay, third energy level. There. And there. Any others? Yes, there are in that D block. So these guys, even though this is period 4, it is energy level 3 because we have to subtract 1 from our D block and we subtract 2 from our F block. So that would make this a 4. Actually, I guess I should have gone up here to do my 4 as well. Am I done with my 4s? No, I got to come down here to my F block and put in my 4s as well. All right, I am not going to fill everything in, but we know that these are 5s, 6, 7s, 5, 6. We know that this is 5 and 6, and this is 5 all the way across. So you guys can fill that in if you want to on your own, but those are energy levels. Next one I want to get to is my L. And remember, that's just going to be S, P, D, and F. So for my L, all I have to do is remember 0, 1, 2, 3. SPDF, the 0, 1, 2, 3. So all of these guys in this section right here, what am I going to say for my L? What am I going to say? 0. That's it. 0, 0, 0, 0, 0, 0, 0, 0. All right, for the P over here, we know that these are all going to have L's equal to 1. It's the easy one. We could race. I'll race y'all. There. I don't know if I won or not. And then for your D's, all of these are going to be 2s. I'm not going to fill in everything. But just realize that those are all 2s in there. All for your D block, that's going to be a 2. And for your F's, you're going to have 3s everywhere. Yeah. So the question is, down here in our D block and our transition metals, do we have to worry about, and I'm assuming you're asking about the energy level. So you do have to subtract the 1. So just like we have written in black, something like this right here, even though it's the 4th period, you have to call it energy level 3. Okay. And so now we get down to our third quantum number, which is our M sub L. And so our M sub L, remember, is going to be anywhere from negative L to positive L. Negative L to positive L. So again, you get back over here to the S's, and it's pretty darned easy. It's going to be negative 0 to positive 0, so you have really no options. They're all going to be zeros for your M sub L. The P's, anywhere from negative L to positive L, so negative 1 to positive 1. Negative 1, 0, plus 1. Negative 1, 0, plus 1. It is going to be that way the entire way down. Negative 1, 0, plus 1. Negative 1, 0, plus 1. So maybe the way you're envisioning this is you're thinking about that orbital spin diagram. Negative 1, 0, plus 1. And when we come back, negative 1, 0, plus 1, that's going to have to do with those arrows in the magnetic spin, so the plus or minus 1/2 that we're going to talk about here in a minute. For our D block, anywhere from negative 2, negative 1, 0, plus 1, plus 2. It should always be where you can repeat it. Negative 2, negative 1, 0, plus 1, plus 2. So all of those are going to be the same. And then finally, your F block goes from negative L to positive L, so negative 3 to positive 3. All right, so our very last one now is going to be our magnetic spin. And for this, all we're doing is we're thinking about those arrows that we mentioned right here, for example, for our P block. If it's an up arrow, the first half of those from that sublevel that are put in there, if it's an up arrow, it's going to be a plus 1/2. If it's a down arrow, it is going to be a minus 1/2. That's all there is to it. So all of these guys, oops, it's not writing very well. All of those, your alkali metals, all have plus 1/2. Whereas your alkaline earth metals are all minus 1/2. Etc. If I were to go over to my P block, I would see, just like we saw from that orbital spin diagram, that all of these guys are going to be the plus 1/2. Then all of these guys are the minus 1/2. So up, 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 down, down, down. All right, and then our D block, to that halfway point until you start repeating your M sub L's, all of those are going to be your plus 1/2. All of these over here are going to be your minus 1/2. And same deal with your F block. These that I'm boxing in are all the plus 1/2. All over here are the minus 1/2. Okay. Okay, so now what I want to do before I let you guys go to work on your homework, I want to just do a couple practice problems. Let's go back maybe here. Your homework asks a couple different, it asks some questions in a couple different ways. But one of the things that I want you to be able to do is come up with 4 quantum numbers for the highest energy level or highest energy electron within that atom. So for example, if I were to ask calcium. Calcium I see is right here. So if I were to assign 4 quantum numbers for calcium, first of all, what's going to be your first quantum number? It's your energy level, so what are you going to say for that? 4. Okay, after that you need to say something about the sublevel, SPDF, but it's quantum numbers, we don't put letters in there. So which one is this, SPD or F? S. And for S, what quantum number do you assign? 0. Well, our third one, M sub L, is anywhere from negative L to positive L. So negative 0 to positive 0. So that's just going to be 0. is calcium, if I were to do an orbital spin diagram, would that very last electron be an up arrow or a down arrow? Down, so it's going to be a negative 1/2. I'm going to do one more, and then let you guys go to work on your homework. Let's say, let's go to cobalt. Cobalt, right here. So cobalt, a little tricky, this first one. Anybody think they know what the energy level is going to be? 3. It is 3. Even though this is in the 4th period, it is, for cobalt, it is going to be 3 for your energy level because you have to subtract 1 for your D. What are you going to say for your second quantum number? 2, because it's in the D block. Third quantum number. And it's going to be anywhere from -2, -1, 0, +1, +2. That's halfway. -2, -1, 0, +1, +2. So it's going to be a -1. And then tell me about your last one. Is it an up or down arrow? Down arrow, so it's going to be -1/2 again. All right, that's it. So nicely done.